Well, thank you so much for the invite, Adam. It's a pleasure to see you again. It's been a minute, so I appreciate having a chance to catch up and present on some of the work that we're doing. I think it's pretty cool stuff. Today, the title of my talk is Materials Informatics Moving Beyond Screening via Generative Machine Learning Models. And I do want to start because, as you all know, I don't do any of this work. I have the awesome opportunity to present it, but it's really done by these amazing people. And I want to point out in specific, these people in green, Marcus, Michael, and Zara are the ones whose work that primarily I'm going to talk about today, but it was some other folks as well. Okay, now I want to say, I love to show this slide to ask people, what do all these materials have in common? And you might look at it and be like, oh, gosh, that's all sorts of stuff. You got artificial sweeteners, you got super glue, you got Vaseline, insulin, on and on. Like, these don't seem like there's a common thread here, but there is one. And the common thread, first off, these are useful materials. And second, they were discovered by accident. We love to think that in material science, we're all about developing new materials. But when it comes down to it, as often as not, it's sort of an accident. It's sort of, we get lucky when we find a cool new material that breaks the mold. And certainly that's the case with all of these. And we can go through some case studies to talk about that. I love to sort of show this to people. Think of like the discovery of the light bulb, right? Thomas Edison gets the credit here, but we know it wasn't Thomas Edison. Yeah, it was previously discovered by somebody else. It was just really bad, right? That light bulb filament stayed lit for not a long enough time to actually be useful for anything. And Edison really tries to solve that problem, like the filament. How do you get one that will stay lit for a much longer period of time? So he's trying all sorts of stuff. You read his quotes about this and it's just kind of ridiculous. He talks about how he ransacked, that's the word he used, that he ransacked the world's fibers, trying to just try them all. He says that he tried over 6,000 different plant fibers. He pyrolyzed them, right? He heated them up in the absence of oxygen and made little carbon fibers out of them. And nothing worked until one did. And he talks about how great it was. He uses this language like, other people would have given up, but not me. Oh, it's just, you can barely read it. Anyways, so that was Edison's approach. He sort of coined the phrase, it's 1% inspiration, but it's really 99% perspiration, right? You got to work for it. You got to grind. And that's one way to discover materials, I guess, right? Is just grind. Is that a way that will work for us facing the challenges in the 21st century? I don't think so. We face big challenges. We got to discover materials way faster. It doesn't matter how many grad students you're going to hire. We need a better way to find things than just brute force is one approach. So then you could say, well, all right, what other ways are there? And maybe it's about just being at the right place at the right time. That was certainly the case here. You got Roy J. Plunkett at DuPont Chemical in I forget the year 50 or something. They're looking at, they had a polytetrafluoroethylene is what they ended up making, but they started with tetrafluoroethylene gas in a cylinder. They had been using it for something. They come back the next morning and they turn the stopcock to get the gas flowing and nothing comes out. So they pick it up and it's still heavy. So they know it's still got material in it. It's not like it got left on all night or something. And so now he's curious and they do something crazy and they just take the valve right off. They just like unscrew the valve of a pressurized cylinder, which is nuts. And then when they don't find anything, they do something even crazier. Take a look here. You can see this. They saw this thing in half with a hacksaw, a pressurized cylinder, like do not try this at home sort of thing. But fortune favors the brave, I guess. And they figured out that you can, there was this white powder in there and it must have polymerized. And we had the birth of Teflon, and holy smokes, we've got that all around us right now. You could say that maybe when it comes to discovering new materials, we're going to rely on nature, take a page from nature. That was certainly the case with de Mestral, right? He was in Switzerland in the 40s. His dog was getting these cockleburrs stuck in his fur. He got annoyed at it, and he's like, oh, maybe there's a good way to actually fasten things. The sort of hook and loop approach was discovered with Velcro there. Or discovery of chrome, right? Chrome alum or chrome alloys, right? This is stainless steels, right? This is all about having a keen eye for detail. As the story goes, in the early days of steel manufacturing, it's a fascinating story. It's all happening in England. And Harry Brearley's in Sheffield, England, and he's trying out lots of new things to try and make gun barrels, right? Back then, the steel they were using were causing cracking and breaking, so he's like, no, this ain't gonna work. So he's trying new alloys, and when they don't work, he's putting them in the waste bin. And he tries one, and it was unremarkable as a material for a gun barrel, so he skips it, but he comes back a couple weeks later, and it hasn't rusted, and everything else was rusted. He sees some speckles of shine as the story goes, right? And so he's looking back in his notes and he realized that, well, that was an alloy that had over 13% chromium, and thus we have the birth of, he called it, they call it rustless steel, I think is what they called it originally. We know it now as stainless steel, right? And not just a keen eye for detail, maybe it's a keen ear for detail. I love this one. Maybe, I'm surely everyone here knows what a shape memory alloy is. You've seen these things. You change, they're processed at one temperature, you heat them up or cool them down, and they can have a martensitic transformation, which causes them to change shape. You can make glasses out of these that then bounce back to shape, all sorts of cool things. Well, how were they discovered? This was in the Naval Ordnance Laboratory here in the United States in the 60s. This guy, Bueller was his name. He's working there and he's making like missile domes for missiles, basically. And I don't know why this was the case, but the ASTM standard they used was to take the dome of metal as they sort of processed it and drop it on the floor. And if it clanged, then it was good. And if it thudded, then it was bad. So there's your ASTM for you in the 60s. So he's trying this and he's just trying alloys. So he's buying books and saying, well, here's a bunch of alloys people said. He comes across one roughly equivalent mixture of nickel and titanium, equimolar, right? He makes it and it's still warm from being out of the furnace and he drops it and it makes one sound. And then he lets it cool down to room temperature and it makes a different sound. And so he says, oh, maybe there's something going on here. There must be a phase transformation happening somewhere near room temperature. And he sort of files that away and doesn't think anything else of it. And it's not until a couple years later that he comes back to it looking for fatigue properties. He tries it, and get this, his advisor at work, some officer comes in with a lighter, sticks it on this material, and spraying it bounces back to shape. And we have the discovery of shape memory alloys, right? So on and on. I'm going to, for the sake of time, I'm going to skip through these because they just keep going. And they're just, one is crazier than the next, but it's all accidents, all sort of like happenstance. You're not designing for it, even cream cheese, right? So, I mean, the point here is that, really we need a better way to discover materials. It's fun to see these accidental discoveries. It's exciting, but it's not a way that is going to address the challenges that we face. So this is the hypothesis, right? The big question that was sort of posed about 10 years ago, about 15 years ago now, was, can data science, if we leverage data science, which was burning up every other field at the time, can we use it to also help us with materials discovery? Will it actually accelerate this pathway? So nowadays, fast forward 15 years, I think the answer is pretty unequivocally yes. It is doing a lot to accelerate the discovery of materials. We already have materials which we would not have had it not been for applying these data science techniques. One of my favorite ones is this aluminum alloy, because it was from Teresa Pollock's group and others, HRL and a few others at UCSB. They used data science to develop a new for the first time ever, a 3D printable aluminum alloy that had the properties they were interested in. And they did this by basically pre-screening via data science for the right compositions as opposed to just brute force trying everything. Here's one from my own research. So I want to share a success story for where we've tried to do it, right? So if you don't know what this is for drilling holes. Elon Musk prattles on about this. This one's actually named Nanny, right? This thing is somewhere under Los Angeles drilling a hole right now, right? They're with dreams of a freeway. Regardless of what they use them for, if you want to drill through the earth, whether it's for gas and oil exploration or for underground freeways, right? You got to have something that's going to cut through rock. So you got to have something that's harder than rock. And at the tip of this thing, on the tips of these cutting inserts, these are very hard materials. We call them super hard materials. And the materials out there for super hard materials, well, there's not that many to pick from. You've got diamond. That's an amazing material, but it's also bonkers expensive. We're obviously not going to use the gemstone quality ones like on the one on the left here. Instead, we're going to make synthetic diamond by taking little tiny bits of diamond and consolidating them together with a metal binder like cobalt. This process is fascinating. You want to learn all about it? Check out our podcast. You can hear all about this amazing guy who grew up in my hometown, Tracy Hall in Ogden, Utah. Crazy guy, went to GE after World War II and basically started helping them. He invented the belt press, which allowed them to achieve the high pressures and temperatures needed to make the first polycrystalline diamond. And what's he get for his trouble? He gets $10. He's so dissatisfied with that he quits and goes to BYU, Brigham Young University, just down the road from us, and becomes their VP of research, where, now GE owned the patent on the belt press, so he can't use it. So what's he do? He invents something even better. This cubic, the cubic anvil, he invents that there, and it's even better. But, so you can make diamond. You can make polycrystalline synthetic diamond for cutting tools, but it's not like it's great. It is crazy expensive. Look how big that tool is. All of the dies that come together, these are all tungsten carbide. If it breaks, you're out 20 grand just for your die set. It is no joke. The temperatures and pressures that they work at are just extreme. We would love to find a holy grail would be a new super hard material which doesn't require these high pressures and temperatures. So what options do you have? You've got your first class of super hard materials that have been known for a long time, diamond and diamond-like heterodiamond, right? Things like these. These are main group elements, leveraging covalent bonding, strong bonds. But about 15 years ago, Kaner's group at UCLA freaking turned the world on its head when they discovered that there's other super hard materials out there that don't require high pressure, right? They basically found out if you mix a transition metal with a main group element, many of these can achieve super hard properties, and you can do it without pressure. You can just arc melt them and you get extremely hard properties, right? So it seems likely that maybe more are out there. 15 years ago, we've discovered a new class. Maybe there's more out there. How are we going to find them? So this is maybe a good place to try and apply data science, right? So machine learning is going to help us in this case try and discover new super hard materials. Well, and I'm sure you've all heard it, so I'm not going to bore you to death, but if you've heard them talk about machine learning, then you know that the general flow is we need the data, we need to featureize the data, we need to come up with a model, and then we have to validate our model. That's the general flow. So where's the data going to come from here? And what data is there? Well, the problem with hardness is that there's like 10 different ways to measure it. There's shore hardness, Knoop, Rockwell, on and on, Brunel, like it just goes on. There's all these terrible ways to measure hardness, and they don't even have the same scale that they report the value on. So if you tried to gather data from literature, you're going to run into the problem of highly what we call heterogeneous data. Just it's all over the place. So that's not a good option. Well, there is another option we could look at. If you look at hardness on the y-axis here and plot it against bulk modulus, what we see is that there's a general trend. It seems to be that materials that are hard tend to be also incompressible, meaning high bulk modulus. Not all of them. Osmium, classic example, simple structure, it actually is not rigid, right? And so bulk modulus isn't enough, but a clever guy, he might have been at Alabama. Chen might be at Alabama. In any case, Chen in 2011 figured out that there's actually a better relationship. If you plot hardness against bulk modulus, that's okay. Shear modulus is better. But if you combine the two in this funky sort of empirical relationship, you get a really good measure of Vickers hardness. So hot dang, if you got bulk and shear modulus, we can calculate those things. There's whole databases, things like Materials Project or OQMD or AFlow, right? They've got a fair number of those calculations, which are not perfect, but not bad either, right? For example, this was as of a few years ago. The numbers are higher now, but when we did this project, there was about 70,000 inorganic compounds in the Materials Project, about 5,000 of which had the elastic tensor, meaning bulk and shear modulus, that we could train from. Now, if we looked at those, half of those compounds were either far from the convex hull or they didn't correspond to an experimental structure, so they were hypothetical. We decided in this case to throw those out. That cut our data in about half, but it still left us with about, a couple thousand data points to train from. So now that we've got data, we have to featureize it. If you know anything about materials informatics, you know that there is, some of the hottest research happening in this area is in representation. Like, how do you represent materials so that a model can learn from it? And there's sort of two main ways to do it. You can use the composition, meaning you give it the chemical formula, and from that chemical formula, we extract some big vector that encodes all the chemistry that you could for those individual elements in some combination based off of the chemical formula. That's what we call a composition-based feature vector, and our group has done a lot of the pioneering work there. But there's another approach, which is to rely on structure. If you know the crystal structure ahead of time, well, heck, you can look at bonding and orientations and all that jazz, and you could turn those into a feature vector, right? And there's clever ways to do both of these things. In this case, we decided to look only at composition because we were interested in materials discovery, where we weren't going to know the crystal structure in advance. And so a structure representation that relies on that structure, it wasn't as interesting to us. So we were just using composition. And the things are like the stuff that you'd expect to see: atomic weight, number of valence electrons, electron density, all this jazz. I think we gave it like almost 200 different features. And then you down select, you do what's called dimension reduction. You throw out the features that aren't useful, and you just keep the ones that are useful for our two different models. So when you're building a model, now that you've got features, you've got data, and you featureized it with chemical, data, you need to find patterns in your data. That's the whole way that data science does what it does, is by finding patterns in your data. So how do you do that? There are so many different algorithms to choose from. You've got random forests, you've got support vector machines, you've got neural networks. Back in the 80s, random forests were the bomb, and then 90s SVMs showed up and people loved those, and neural networks actually showed up in the 80s and then they sucked and no one liked them, and then they came back and they've made this resurgence in the last 20 years. The point is that it doesn't matter. These are all essentially doing the same thing. They're finding patterns in your data in different ways and allowing you to then use those patterns to make predictions, right? So in this case, I think we did a support vector machine because we only had 2,500 data points, and that's right around the cutoff of when neural nets start to outperform SVMs. But we went with an SVM on this one. So now we can see how well we do. And this is what you see. You've seen plots like this. On one y-axis, for example, you're seeing the predicted value. This is the output from the machine learning model based off of patterns in your data. And on the x-axis, you've got the training the training set, right? So this is stuff that it was able to train from, so it's the right answers. If it was perfect, we'd have all the data right on this 45-degree line, but we don't, right? But it's not bad either. I mean, think of this. Look at the metrics, right? The root mean square error. That means that if you take the square root of the average error, it's about 17. Well, let me ask you this. Even if you're an expert in mechanics, could you predict within plus or minus 17 of the root mean square error the bulk modulus for any chemistry that I give you? No way. Not your best grad student, not the best expert in the field could get even close to that kind of performance. This is fantastic, even if it's not like as good as DFT, which it isn't, right? Because we trained off of DFT and we're only going to add error to that. It's still not bad. It's pretty darn good, actually, right? And so we use this now to screen. And this is where we see that really the quantum leap in what machine learning has to offer for us. We were able to then say, all right, of all the materials that have been made before, meaning they're in some sort of crystal structure database like the Pearson or the ICSD, let's go ahead and look through there and let's screen for all those to figure out what their bulk and shear modulus would be. And we looked at stuff that would be a nightmare to try and predict with DFT. F electrons, disordered structures, big unit cells, doesn't matter. We can predict those all the exact same. We calculated over 100,000 compounds on this dorky laptop in like no time flat, right? And here's what we get. So what you're seeing now is the predictions with their errors. Like remember, each one of these data points technically should have like a little plus or minus 17 or whatever it is, gigapascals error on it. They're not perfect, but they're pretty close. You're seeing your predicted rigidity on the y-axis, shear modulus, predicted incompressibility on your x-axis, right, your bulk modulus. And if you look in, we know that the materials that are going to be super hard are going to be the ones that have high values for both. And if you look in that region, sure enough, all the sort of known super hard materials are in that region. It's good. But there was a couple that weren't sort of known, right? This rhenium tungsten carbide, this moly boron tungsten carbide. These things, nobody had measured their hardness before. And so we decided to make them. Sure enough, we can make them with just arc melting. We don't need high pressure to make these things. With a little bit of effort, we get them phase pure. So we know we're assessing a single phase here. And we can measure their hardness and voila, check it out. At low loads, we just crossed the threshold of 40 gigapascals. That means it is officially a super hard material. What's exciting about this is that this whole process took us about 6 months, right? We went from knowing nothing about this field to discovering two of I think these are both top 10 hardness materials ever discovered in about 6 months. I mean, that's the promise of machine learning. It reduces your compositional space from, needle in a haystack to just a couple handful of needles, as Citrine likes to say. And I think it's true. This is a clear example of how we've been able to find materials. What's kind of funny is we actually went to publish this. We ended up getting it published in JAX, which I'm excited about. But when we tried it first, the editor's like, yeah, but you didn't validate your model. And it's like, what do you mean we didn't validate our model? He's like, you predicted bulk and shear modulus. You measured hardness. I was like, who cares? They're related. He's like, no, if you want to publish here, you got to validate. It's like, oh my gosh. So I don't know if you've done this, but measuring bulk or shear modulus is a nightmare. It's so hard. Here's how we did it. We had to take our sample and load it into a diamond anvil. You ruined two perfectly good diamonds, right? I was actually at De Beers buying these diamonds. It's a bizarre world. You put a little steel gasket. You squeeze on your sample inside of there with some sort of pressure medium, right? And a calibration standard, something like platinum with a well-known equation of state. You squeeze on this stuff and you just monitor diffraction. So what you're seeing here is Q, that's our diffraction data as a function of pressure. As you squeeze on it, you can see the peaks shift, right? They shift, to the right because they're getting smaller, right? So you're getting smaller unit cells and you can just track that volume of your unit cell as you squeeze it. In fact, check it out. This V over V naught, that's the instantaneous volume divided by whatever your initial volume was over pressure. And you see, the big surprise, as you squeeze it, it shrinks. Well, if you fit that curve with this horrific equation, the Birch-Murnaghan equation of state, then you can actually extract the bulk modulus. So it's a lot of work. It took at least 7 months. It took us longer to validate it than to predict 100,000 compounds and find two new top 10 materials, which is bonkers. Anyways, what do we find is that we were spot on. The predicted value was 370 on the left, and the experimentally validated one was 372, with some small error. Same thing in the moly tungsten boron carbide. We're about 400. We experimentally found it to be about 380. Pretty darn good. So anyways, we get this published. Pretty exciting stuff. But the critic in me would say, and the critics out there in the world also say, cool, but you found a couple transition metal borocarbides and said they're new super hard materials. And they are. Nobody measured them, but they're also kind of uninteresting because they're transition metal borocarbides. We already knew that those things are probably going to be hard, right? And so this is sort of this broader theme with materials informatics is, can it actually learn something new? Can it extrapolate? Or is it only ever going to tell us sort of limited utility in that, it's related to these things and we can predict the values. That's a very different thing. Predicting something entirely new is a lot harder, right? But data science has done this sort of thing to predict things that are entirely new. This is from an old now article from New York Times, but they're basically talking about how AI can generate faces, right? If you give an algorithm a bunch of faces to train from, it can now predict faces. It can generate faces and with generative models. And take a look at this one. It tries to trick you and it says, which one's computer and which one's human. and they're actually both computer. Like these are both made by a computer, which is pretty wild. And these are made with the so-called generative adversarial network, which I'll talk about, which is basically pitting two neural networks against one another. Essentially, you have one neural network which is generating something, and then you take a bunch of real images, and now you take your fake one and your real ones, and you give that to another network, which tries to discriminate, try and pick which one's fake, which one's false, essentially. The magic here happens when you tie those two neural networks together. If they're tied together with a custom loss function that forces the one to get better as the other one gets better, then they train against one another, and you start to get really, your first faces that come out are pretty bad, but you start to get really good ones. And the grad student, because this was a grad student who discovered this I think it was at University of Montreal, Ian Goodfellow is his name. I love this sort of slide that he shows. He's showing you the progression of GANs over time. From 2014, they made some, they look like faces. They weren't great. And then 2015, they're getting better. 16, 17, 2018, holy cow, we're getting good. These things were looking amazing. And then, StyleGAN, the one on the left, that was the end one here. The one at 2018, that was StyleGAN. And it was amazing. It does these high quality, high resolution images that look like, that's not a real person, but you'd think it was. But one of the problems they had is things like texture sticking, where if you can make these faces move, right, you can map them over to latent space, where like a different part of the latent face is looking this way and a different part is looking here, and you can actually map the transition so you can make these things talk. You've all seen the deepfake videos. This is the underlying technology there, right? One of the problems they had with StyleGAN is that when it would move, like the small details would stick. So like the beard would sort of like hover, and the face underneath it would move behind it. It was kind of unnerving to watch. They fixed that now with alias-free GAN. This is an NVIDIA development, which is just stupid good. And they've done other crazy stuff like style transfer. Style transfer can be done with GANs, where you train a bunch of images with a certain style, then you freeze that network, and then you send a new image through that pre-trained network, which has a sort of certain style, and it filters the incoming image with that style. Like here's a picture of me and my totally adorable daughter being filtered in different ways based off of different images that they trained the style transfer network on. Pretty amazing stuff that they can do there. They've done it with not just faces, but obviously this is not a real image. It was just trained off of Google Street Images up in the Alps, I guess. They can do some pretty remarkable stuff. I like to point this out because it was my grad student, and Ryan Murdoch, who now works for Adobe doing the same thing. He got interviewed by Digital Trends because he built a tool that does the inverse of Google image search. Normally image search, you type in a query and it gives you images, right? Well, this is like that, but this provides images that don't exist. Google crawls the internet and says, I found these images that look similar to the word embeddings of your text query. His actually generates the image in real time based off of your text query. So the one here in the middle the text query was an intricate drawing of eternity. How about that? Isn't that cool? How about this one on the right? The text query is a strange ghostly figure in the forest. Or this one, hungry dogs will devour in the daytime, right? If I haven't convinced you yet that it looks kind of like machine learning can maybe start to predict some things, I don't know what will ever convince you. I think it's pretty convincing. But the unanswered question is, in material science, is it going to be able to predict new things? Can we generate new things here? Right? So to answer this one, it's a little more challenging, right? The same tools that we used before won't work here. We're going to have to get a little bit more creative. So we sort of ask, can we generate these things? And the reason we want to do this, because again, going from like screening is one thing. And I would say that what most people have done is screening, where they take some sort of known database where they don't know the properties. They build a model trained off of data, and they basically learn how to predict those properties. That's what I showed you earlier with hardness, right? With bulk and shear modulus. But what we really want for discovery is to go beyond known materials out to totally unknown materials and do the same thing. Find those unknown materials, figure out what their properties are, predict them before you ever have to make them in a lab. So to do that, it's going to require generative models, right? And some of this has been done before. We're certainly not the first people to do this. There's been some cool models, right? Genetic algorithms. Maybe you're familiar with this, and I love this thing from Simpsons. How do you make Timmy? You take a bit of mom and a bit of dad and you get Timmy, right? Well, that's kind of the idea behind genetic algorithms. If you got a couple different crystal structures, which admittedly are different, well, you can combine them together in different ways. And, there's been a lot of work on that over the years. But moving now more towards machine learning models, there are sort of 4 or so main ways. You can use a variational autoencoder. It's a type of generative model. It takes an input and maps it over to the so-called latent space. And from that latent space, you can now just pick a different part of your latent space, and it will decode that to something that looks kind of like your input, but in a different part of the model. There's GANs, which I've already shown you for images. There's reinforcement learning, which basically builds on the evolutionary algorithm approach. And then there's sort of combinations of these. And there's been some great papers over the years. But I will say that the vast majority of work that's been done here has come from our friends, the chemists, who have done it on molecules. And there's a big reason why they do that. Working in molecules is easier. It's way easier because you don't have to worry about periodicity. Periodicity is really challenging. Periodicity makes it so that the representation tool that they can use in molecules can be far simpler to be invertible because they don't have to worry about periodicity. When you introduce periodicity, it makes it way harder, and there's just not a good solution for it right now. Sure, you could do it like this, where they've basically said within the titanium oxide, I think is maybe this was vanadium oxide, I forget what it was. Within some small system, you can do slight changes using a VAE, a variational autoencoder, and technically find something new, but it's not like a majorly different crystal structure. It's like a slight variation on a known one, and yeah, they've done it, and it's kind of slick. Some people have tried to do this with not great success. Anyways, so we had an idea. Here's our idea. We said, God, this seems like an interesting area, and it seems like an important problem to solve if we're going to actually start generating new materials. And my student had this idea that was wild. We've been reading in so many sieve cards in this process. They know that all the information for a structure is in that sieve card. So then we started thinking to ourselves, like, well, what if we just tried to learn from that sieve card directly, right? What if we tried to predict the stuff in that sieve card? If you did that, then you could generate a structure, right? If you could do that accurately, you could generate a structure. So that seems kind of interesting. Maybe we can give that a shot. So we wanted to do that. And so we set out with the couple different research objectives to sort of try and answer this question. First of all, is it possible, right? And then as we did it, we would try and compare what are called traditional GANs, these generative adversarial networks, with so-called Wasserstein GANs. More on that in a moment. We also wanted to try and predict only materials that would be stable, right? So things that would be thermodynamically feasible to actually make. It wasn't as much of an interest to us to make things that were totally hypothetical structures. And then lastly, can we do this better by doing something with a modified atomic number? More on that in a moment. So I think this has some unique aspects to this work. First off, we're not going to constrain our data set in any way other than ensuring that the sieve files represent real crystals, right? We can say that we're going to, well, let's see, we didn't have to use materials properties. This is strictly based off of structure, which is a pretty big difference in how a lot of these have been done. So we're not necessarily looking for a certain property, but we could tag that on afterwards. Right now, we're just trying to make new, stable looking, interesting materials, right? You could always add materials properties on later. If you wanted to do a conditional GAN, right, you can do a conditional GAN, which adds some sort of target regressor value at the end. So this is our model main approach, right? So we've got chemical white space. We're going to say, look at any sort of combination of elements, like try it all, right? We're going to send those, we'll start with random noise, right? In this space, we're going to send it through our generator, and this will produce what I'm going to call fake unknown compounds. We don't know if these are even real or if they're likely or anything. So the very first step that we wanted to do was send that through a convex hull distance calculation. Are these things even remotely close to the convex hull? Because if they're not going to be thermodynamically feasible. So we can take these unstable compounds and just toss them. The ones that look like they're stable, now that we have the sieve file, we can do this calculation with this blue circle is a machine learning model. There's been several that are out there published. So we can do these very fast, these calculations. We now have fake unknown compounds, which we hope are stable. We can compare those with real known compounds from some sort of database like the Pearson and put these to our discriminator and have it learn which one's fake and which one's real. It'll then do a classification, 0 or 1, depending on whether it thinks it's real or fake. We tie these two things together via a custom loss function and backpropagation so that as the generator gets better, the discriminator must get better. And as the discriminator gets better, the generator must get better, right? That's the idea behind what we're trying to do here. So what sort of information, when we say that in comes, noise in our information, what information does our generator need to make a crystal structure? Well, if you look at a sieve file, it's shocking how little information it needs to generate a crystal structure. You need the lattice, you need to know what type of lattice it is. So you need the lattice parameters, you need to know the angles, you need to know the space group to know what symmetry operators are going to be applied to it, right? And then you need a basis. That's it. From what? That's like 10 things here. You can reproduce a crystal structure, which is very complicated, which has periodicity. It's ordered, right, for a long ways. And you can do this with a very small amount. So the stuff that you actually have to predict is the pink, the green, the blue, and the yellow stuff, right? That's what you need to figure out how to predict from your GAN, which is not that bad. So if you're going to actually do this training, big props to people like the ones who made PyMat Gen over at Materials Project. We couldn't have done it without them, because we have to take all those CIF cards and pull that stuff out for hundreds of thousands of cards to have training data. You can do that pretty easily with PyMat Gen. Big props to the people at Pearson Crystal Database, ICSD, pick the one that you like. We like them. They have a huge database with pretty well curated. I had some 300,000 CIV cards. Of course, when we went through it, we had to throw out almost half of those because they were incomplete. Oftentimes, they don't have the basis. They know the crystal space group, they know the lattice parameters, but they don't know the exact positions of the atoms. So we threw out ones that had an incomplete basis. But that's the training data we had to train from. And now you have to think about, okay, how are we going to represent this? You could just do a matrix, right? Just think of one row in this matrix. You've got your lattice parameters, A, B, C. You've got the angles between those different, directions, alpha, beta, gamma, the space group number, and then you have to have as many columns as you might eventually need to represent materials that have, diamond, you have one atomic position and you define diamond. But some of these silicate MOFs, holy cow, they need like 200 unique positions in their basis. So this matrix needs to be as large as whatever your largest thing is in your training set. So for us, that was, I think, 200 potential unique elements in the basis. So what do you do for the things that don't have that many elements? We fill it with negative ones. You could do zeros, but negative ones we found actually work a little bit better with the GAN structure. So we fill in with negative ones, and that's basically us telling the model nothing's there, ignore it. Now you'll wonder why are we doing this 7 different times, right? Well, we do that 7 different times for every prediction because it makes it more stable. If you rely on a single prediction, A, B, C, alpha, beta, gamma, if you look at all these across 7, they tend to be sort of hovering around certain values, but they're not the exact same. We found that it was much more stable if we averaged across 7. Why 7? It's the number we tried. I think we tried a few, but we haven't optimized that by any means. But it certainly seems to work, okay? So that's how we're representing our data when we actually feed it to our generative adversarial model, okay? Now, we did have to put a couple constraints on this. If we just let the model predict whatever it wants, it will do some crazy things that are not allowed by symmetry. For example, it will say that the space group is over 195. Those are all cubic. But it then will say that alpha, beta, gamma aren't all 90, A, B, C are not equal to one another, and that's not allowed. So we did have to build in some constraints. We had to say round it so that they're all roughly equal to each other. Round these values to 90, right? You have to enforce a few things like that. Interestingly, you don't have to do it very much. They're pretty close, right? They may not be exactly equal ABC, but they'll be very close to one another, right? Because it's learned that from patterns in the data, but we did nudge it to complete it. And we had to do that for all these different space groups to make sure that we weren't violating symmetry. Okay, so we can predict things. The other question is like, okay, when it predicts an element, right? If we go back to our representation, right here I wrote like helium and hydrogen, but we don't typically do that because neural networks and machine learning models don't work well with strings. We always represent things as a vector. So what's a better way to represent a individual element? Well, you can use a scalar. You can use the atomic number, right? So helium has an atomic number of 2, for example. So instead of writing helium here, we put the atomic number 2. But that means that when it predicts something, it's going to regress it. It's going to think that that is a numerical, right, as opposed to a categorical. So it's going to predict numbers that are in between. Like it's going to say, I think these are your elements present in your formula, right? And an element with atomic number 13.44, well, what is that? One approach would just be to round these things, right? You could just round them to the nearest thing. But a bigger problem is the fact that no material has 10 different elements. If you're familiar with Pauling's rule, one of his rules was parsimony, which basically said things tend to have few different elements, right? By the time you're getting to like quaternary or quintenary, however you say that, right? It's not very likely. So we needed to do something that took the 20 positions and made sure that there weren't 20 different unique elements. So we can do that with clustering, right? We can cluster things together. We can collapse them down. And so all these materials are sort of similar. You can sort of collapse them down to aluminum, scandium, aluminum, for example. And then you've got 3 distinct elements, maybe on a bunch of different positions. That's fine. But different elements should be limited. And that's one way to do it. So in the early days when my students started doing this, I was like, oh, let's give it a shot. I don't think this is going to work, but give it a shot. Here's what he did. He built a couple sort of vanilla versions of GANs that he pulled off of Hugging Face and whatever else, right? And they were so bad, we just about quit. Like, look at this one on the left. That's just a gumball machine. It is just a mess. You've got atoms overlapping. You've got 20 different atoms. The loss curves are out of control. Like, this was so bad, we about gave up. So he tried a few other things. He introduced batch normalization. He had convolutions. It was okay. It was still not good. Then he added LSTM layers. If you're familiar with LSTMs, this is for recurrent neural networks. It's a way to take in sequentially data. Adding LSTM layers made pretty big improvements, but it was still, my goal at the outset was to try and trick some of my chemistry buddies to say, hey, is this a real material? Or did my GAN generate this? And this isn't fooling anybody. If this is what we showed you, this isn't fooling anybody. And the problem has to do with the difference between a traditional GAN and the so-called Wasserstein GAN. A traditional GAN has this problem of what's called a diminishing gradient zone. If you're familiar with the activation functions here in your loss function, basically what happens as it starts to make a classification, 0 means it's fake, 1 means it's true. As it's starting to make a prediction, this one's fake, this one's true, it uses this sort of sigmoid. This is a sigmoid, right? And so as you get higher and higher numbers, it's more and more confident that that's a true material versus a fake one. The slope flattens. And that slope flattening means that the information that gets fed back to your generator via backpropagation is also diminishing. So think of it like you're running a marathon, and as you get closer and closer to the finish line, you start moving slower and slower. This is what's happening. We were getting things that were intriguing. They looked promising, but it was not training very fast. We were really not doing well because the closer we got, the less useful information got fed back to the generator. So we need to fix that. Clever people have figured out a better way to do this, and it's with the so-called Wasserstein GANs. The major difference here is that in a Wasserstein GAN, Wasserstein comes from the so-called Earth mover's distance. Doesn't matter if you know what that is. But the key difference is the loss function is linear here, meaning that no matter what the prediction thinks it is, true or false, anywhere, even if it's really sure that it's true or really sure that it's false, the information that gets fed back is linear. It's the same gradient, right? So we are able to improve our generator continuously, even as we start to get better and better models or better and better ability to differentiate from good and bad, right? I'm going to skip some of the details here because I don't think people care about them, but there was a lot of work to figuring out. GANs are a nightmare to make work. There are a ton of tunable parameters. There's a ton of things you have to sort of figure out. How you normalize the data is one example of that, and we had to tweak that a fair bit, but we got there. I love this slide. Now, if I told you what elements these were, then you would know that which ones are real, which ones are fake. So we haven't finished it yet, but we're getting there. Just looking at these structures, half of these are real and half of these are fake. I'm sort of showing you 2 glances at each one. Ask yourself, could you pick out which ones are real from which ones are fake here? My initial goal of fooling chemists, right? We're getting to the point where we can actually try and fool them. And I actually presented this at the Solid State Materials Chemistry TSRC Telluride conference, bunch of respected chemists, and I fooled over half of them. Pretty exciting. So the GAN looks like it's maybe able to generate new structures in a way that, they're kind of convincing a little bit. Now, how do we quantify how well we're doing? Well, I can ask people and I can sort of gauge that, but that's anecdotal, right? How do we get quantitative about saying how good is our model? Well, one thing you could do is you could calculate the distance from the formation area. We already know that these things are going to be mostly stable. Let's actually compare those to the real materials and see how they do. Sure enough, they're all negative, right? These all have, they're pretty stable. That's okay. That's not bad. But a cooler way to do it is, what if you tried to cluster the data? What if you take all these things, the outputs of it, send it to real materials, send it to fake ones, have it try and cluster them. If it clearly has 2 clusters where it says, here's your real ones and here's your fake ones, then the algorithm is clearly able to tell the 2 apart. But if it puts them together in a mixed way, it doesn't know which one's which, even using a k-means 2 clustering algorithm, right? And that's what we're seeing, is that when we try and do this, it's mixing them really well, like almost 50-50. It's doing a great job of mixing them. But we decided to try and do even better. One of the problems that we were running into when we were trying to predict these things is like, think of your periodic table, like the atomic number of fluorine is 9 and neon is 10, right? Well, that doesn't mean that fluorine is chemically similar to neon. It's just next to it, because that's one of the many ways over the years that we've decided to do our periodic table. And here's like 4 different ways over the years that people have thought up. In fact, there's been some really clever ways over the years that have reordered or reorganized the periodic table in a way that each number is now putting similar elements next to those that behave similar to them chemically. So for example, going down the periodic table is the most obvious one. This was from a paper in 1984, almost the year I was born, right? Pettifor's modified atomic number scale for the periodic table of elements is a really clever approach, right? Instead of numbering them the normal way, look what he does. He goes down, right? These things are all similar to one another, these noble gases. Then he goes up here because they're all similar. And then he does whatever he's doing. He's sort of tracing through, basing off of chemical similarity. It's a great approach. An atomic number doesn't mean anything, but at least this atomic number has some meaning embedded into it based off of chemical properties and chemical reactivity and similarity. It's not the best way. In fact, 3-4 years ago, in 2018 or 2016, I don't know, whatever it was, 2016, a modified petaphore scale was put out for this exact purpose, where they did a better job of ranking things so that similar are next to similar in terms of atomic number. Pretty clever approach. So you could use these tools instead of just the regular atomic number, and you do better, right? If you look at these numbers again, these things aren't necessarily similar to one another, but with our modified scale, now they're going to be similar. And so you can do that. Here's what we see. If you look at the fraction of the real versus fake in different clusters using the atomic number, modified petaphore and petaphore, we're seeing that we're doing a pretty good job of actually finding things, okay? Yeah, clustering definitely gets improved. It's putting all the things together. It's actually, it's not differentiating real from fake. It's putting them all together. Okay, so I want to save some time for questions. So let me summarize some of the things that we found. This work is still ongoing. We don't have yet the killer app here, but it's certainly moving the right direction. That it's got me excited about it. So here's what we found. Crystal structures do seem to be produced, which are increasingly believable. We get the best performance when we use a Wasserstein GAN. I think that's mainly because of the activation function, the continued improvement that it gives allows us to do better that way. We see the same sort of patterns. We see that it's obeying symmetry. Where we're getting it wrong is that it's still putting atoms too close to one another. If I showed you like a histogram of bond distances or the types of atoms that it's using, and we compared that to actual distributions in known materials, it's off. It's not there yet. So what we're currently working on is encoding not just symmetry, but now some chemical descriptors related to basic things like bonding and overlap and common elements, right? So those are new chemical descriptors which we're adding to this process, which we're doing in the next iteration of this work. I'll say that the GANs were trained without constraints, but we did introduce constraints afterwards on the representation of our materials. And that we're seeing pretty good prediction of materials based off of formation values and clustering. Okay, so with that said, I'm happy to take any questions, and I'll remind you that if you're interested, a couple resources first to point out. First off, if you're interested in more in this area, I'm chairing a conference, and you can still register. It's going to be in Pittsburgh in just less than 2 months. So you can check out AIM 2022. We're going to have a very cool conference dedicated to this idea of informatics applied to materials. You can check out our podcast on any platform. And then the last thing is I have a YouTube series. If you go to just Google Taylor Sparks on YouTube, you'll find that I have a bunch of different playlists, including one on materials informatics, where we go through all the gory details of how to do this stuff from features to data to representations, models, all that jazz. So with that said, I'm happy to take any questions.
Wow, okay. Thank you, Taylor. That was great. Let me go ahead and stop the recording so people can ask all their questions with no fear.